Okay, so welcome to video number 4 in Advanced Fluid Mechanics. Now in this video, I'm going to be covering section 3, which is called Conservation Laws. And this will be covered in the next 2 videos. So I'm showing the topics that I'll be covering in this video in the white text, and then next video, I'll do what's in the gray text. And basically what we're going to be looking at in this video with our conservation laws is how do we formulate equations based on these laws that will then tell us how our fluids behave. And this is very powerful because the fluids have no choice but to obey these laws. And so therefore we can figure out their behavior. And by behavior, what I mean by that is these equations that we're going to derive, when we solve them, we'll be able to solve for the velocity of our fluid throughout the domain we're interested in. And the other variable is pressure. So we'll see we can solve for pressure gradients as well within our fluid. And so we'll know from solving these equations how our fluids flow, how they behave, right? Because we'll know the velocity and the pressure gradients. And we'll see what I mean by that more specifically as we go through this. But also another note before we start here, these laws can be written in 2 ways. So they can be written in the integral form where we're relating it to a volume fixed in space, like a control volume. And that's what I generally cover more in my undergrad course. And they can also be written in a differential form where they're applicable at a point. So that's what I'm going to focus a little more on here. Because at the undergraduate level, I don't really get into the derivations, and we're more focused on how we use the laws and how the fluid's forces are applied to objects, which would be like a control volume. But in advanced fluid mechanics here, I am going to focus more on the derivations in this video. And the reason for that is because at the advanced level, we're likely going to be dealing with more complex situations. So the basic derived equations might not always apply. And so in looking at how to derive them, you'll be able to derive them even in situations that differ from the normal assumptions or approximations we make. So therefore you can add in things that are more complex, maybe different kinds of forces and things like that. Okay, so keeping that in mind, let's jump in here and look at our conservation laws. Okay, so in order to derive these conservation laws, we're going to first look at something called the Reynolds Transport Theorem. And the reason for that is because we're going to frequently need to be able to find the time derivative of integrals over volumes that are moving and deforming. So we'll start with the most simple form of this, which is known as the Leibniz theorem. It's basically the 1D case of this. Okay, so the figure helps make this clear. So we have this line, which is our function f, but it's changing with time, right? So it goes from here to here. Okay, so how do we take our time derivative of the integral? So the integral of the function originally on this figure shown with this dark line, I'll color it in here to make it more clear. That's the integral of f from a to b, right? Because it's the area under the curve. But then as it shifts in time, we see this new time step dt. Our integral becomes the area shown by the dashed lines. And I'll color that one in too. So this equation, when we take the time derivative of the integral, we basically look at these 3 components here, the components that change over time. So the first part that changed, because the function is changing with time, is this top part here, which we can write with this term here. And then we can see we add the part that we gained because point B has moved as well at this rate dB by dt here. We add that one, plus sign under here. Subtract the part we just lost because point A has changed as well over time, so we subtract off this term here. So in summary, we then write the rate of change of the integral, so how much the integral is changing over time, by capturing the addition of the top region and the region to the right and subtracting that region to the left, because that represents the rate of change of the integral. Now, if we want to generalize this for 3 dimensions, we can start by looking at the definition of a time derivative, which I've shown here. And it helps, I think, to have a visualization of this. So we can use this figure at the right here, and we can see how these 2 integrals within these curly brackets here are defined. So we've got this one here, right, which is the dashed one. So our control volume is moving, and that matches this here, the dashed line. And then at time t, we had this integral here, which is where the control volume started out. Now we can expand this by defining our volume increment like this. And Taylor expanding the integrand function with only the first terms of the Taylor expansion, like this. A reminder that I'm underlining it where it's bolded. Okay, so then this term right here, we can use that to simplify. And that's written over here. So we've expanded all of these terms out, right? So for example, we now have our function like the Taylor expansion here, and our next term in the Taylor expansion here, right? So you can see that we've broken it all out like that. And also integrating for our volume increment, which we've defined here. Now we can simplify further if we sub this whole thing in, because this one now cancels with this one, right? When we sub it back in, those two are going to cancel. And when we take this limit right here, both of our delta t's and delta v's will go to 0. So this term right here won't contribute anymore, right? So that will be gone because it's second order. So when we sub that whole thing in, we just end up keeping this term and this term like this. And now our figure is going to help us move forward with this. I think visualizing it is the best way to think about it. So if we have this small area element dA, I'll trace it out here. So over our time delta t, dA will sweep out an elemental volume at this velocity. So B is a velocity, right? So this volume here is actually going to be B delta t times our n dA, right? That's how we get our volume. That's the volume that dA is going to sweep as this thing moves at this velocity b, right? But then this little element of delta v that we've just defined is located adjacent to our surface a star t, right? Like our original surface. So all these elemental contributions to our delta v can be summed together with a surface integral. And then as delta t goes to 0, the integral value of our function within these elemental volumes can be taken as the same as the function f on the surface a star t. So what we can do therefore is we can write that. So this integral here, right, delta v, as t goes to 0, okay, we can have it over the area, okay, that function times that volume that's being swept out. Okay, so we take that limit and then we sub this up to here, right? And then we end up with what's known as the Reynolds Transport Theorem, which I'll definitely box here because it's important. Okay, and it really goes back to the same idea of the Leibniz theorem that we saw above. So basically, the total time derivative of our integral, right, is going to equal the integral of the partial time derivative plus a term that counts for the motion along the boundary, right? So, you know, it seems a little bit complex to follow, but actually it's fairly intuitive, right? So you have the term that accounts for the function changing with time right here. And then we have inflows and outflows of f taken care of with this term here. And the dot product takes care of whether our surface area is advancing, so b dot n is greater than 0, or retreating, where b dot n would be less than 0. So we don't need like two separate terms for that. It'll take care of the total surface area and have the advancing side and the retreating side taken care of with the dot product. And so effectively we see how that d by dt, that time differentiation, can be moved inside to our volume integrals. And that's helpful in deriving the conservation laws. Okay, so that's our Reynolds Transport Theorem. Now let's get to the actual derivations of our conservation laws. Okay, so let's first look at the conservation of mass. Now there are actually a number of different ways we could derive the conservation of mass, which, you know, is basically just saying mass cannot be created or destroyed in our situations, so our fluid has to obey this law, right? We essentially have to have a mass balance anywhere this thing is flowing, right? So the approach we're going to take here is we're going to first write this in an integral form for a fixed region of space, and then from that we're going to deduce the differential form. Okay, and I'm not saying any approach is better than the other. For conservation of mass, I tend to find this to be the most straightforward way to look at it, but I think it's just neat that you see different ways of doing this, okay? Okay, so we have our fixed volume in space. So the rate of increase of mass inside, right, is our time derivative of the mass within this volume. So we write that like this. And then our Reynolds Transport Theorem, actually we can use it right away here, says that we would just end up with this, and I'm just going to put slashes through the v's for volumes here, which isn't needed because we don't have v's for velocity, but anyways, I'll just do it to be consistent. So we end up with this. And we don't have our additional term because it's a fixed volume in space, so it's not moving. Okay, now our volume is fixed in space, so the volume's not moving, but we do still have mass flow rate across this boundary of this volume that we pick. Okay, so to describe that mathematically, the rate of mass flow out of the volume is the following surface integral. And so that gives us the outward flux through our area element dA. And I'll denote this A as a vector, which just makes things easier. So I could also write it as n dA for the normal times the dA. But if I write it as dA with the bolded, that's our vector dA, which has magnitude dA and our direction along the outward normal. Okay. Now we apply the law of conservation of mass. So because mass can't be created or destroyed, the rate of mass increase within this fixed volume has to equal the flow across the boundaries, okay? It has to all be accounted for. It doesn't have a choice. So therefore we can write I write my densities with a little tail there because my past students have told me my rows look like peas. So when I have that little tail, that's like a density. All right, and that is basically our mathematical way of saying any mass change inside this volume has to be accounted for by mass either entering or exiting across the boundaries, right? And so that's our complete integral form right there. But now we want to go to our differential form. And so we can do that by transforming our surface integral into a volume integral. And we remember from what we learned earlier in this course, we can use Gauss's theorem, or known as the divergence theorem, which I've shown right here. So I'll rewrite this term on the right-hand side using the divergence theorem. So we went from this to this, right? And then I can sub that into the conservation of mass and rewrite it like this. I can reorganize it because they're all dVs now. Okay, so that was subbing this right into here for this equation here. But now what happens is this relationship has to hold for any volume, okay? And that means that to equal 0 here, the integrand itself has to vanish at every point. Because if it didn't, we could choose a small volume around that point and we could get a non-zero integral, right? So for this to be 0, everything in the brackets has to be 0. And so therefore, we can write the part in the brackets. And this, we will definitely box. That's the continuity equation. So that's our conservation of mass in differential form. There's different ways we can write this too. So if we rewrite that divergence term there, like this, like if we expand it out, then based on what we have for the material derivative, we can write it like this. Okay, and we can box this one too. They're all forms of the conservation law. Integral form is a very useful one too. But what this one really helps us see is, so this derivative d rho by dt is our material derivative. So that's the rate of change of density where we're following along with a fluid particle. Okay, so the densities change with time. It could potentially be non-zero due to changes in things like pressure, temperature, or composition. That could change the density over time, right? But then we have a description called incompressible. And incompressible means the density doesn't change. And this simplification really helps us a lot, okay? So for the most part, liquids are incompressible, right? So very large categories of fluids are incompressible, which helps us make the math much more simple, okay? Gases are compressible, but generally speaking, for speeds below a Mach number of about 0.3, the fractional changes of absolute pressure in the flow are small, okay? So essentially, density changes in gases can also be small. And generally, you just look at your scenario to see if that's true or not. So if you have a gas, you'll be able to see for your situation if the density doesn't change very much. And then you can also use the incompressibility assumption. So you can say it's incompressible. And what that means is you can get rid of that first term for incompressible fluids and write it in a very simple way like this. Okay, and remember, that's only if it's incompressible, that assumption. Okay, so they're all boxed for different scenarios. So now you've seen exactly how this comes about, right? So that's the one we can use if it's incompressible, and that makes the math much more simple, right? We'll actually apply this throughout this video in a few different circumstances too to make things a little more simple for ourselves. Okay, and what you can see from this equation, what the mass balance gives us here, is it forces our velocity to follow this behavior. So if we have a mass balance, we have a limitation now on what our velocity can do. And so that helps us solve for velocities and flows, right? Because the flows must obey the mass balance. So you can see where we're going with this is now this restriction on what the velocity can do can help us to solve for our fluid flows in different circumstances and see what our velocity profiles are going to look like. Okay, so that's sort of forecasting ahead at how you use the conservation of mass. And we'll look at some of these approximations later on too, when we look more generally at what's called the Boussinesq approximation. But for now, we're just going to look at specifically the different equations we have for the conservation of mass in different scenarios. Okay, now next we're going to move on to our conservation of momentum. But essentially that's going to be a force balance. So before we do that, we're going to look very closely here at where these forces come from. So essentially, like, what are the different types of forces we can have that act on fluid elements? Okay, so we can have body forces, which are sometimes described as action at a distance. And these would result from our medium being placed in certain force fields. So generally they can be gravitational, magnetic, electrostatic, electromagnetic. In the vast majority of cases, they're gravitational. So that's what we're going to look at in this video. But as I mentioned before, because we're going through the derivation, you'll see how the gravitational forces are applied. So if you had, say, electromagnetic forces, you'd also be able to apply those in the same way, right? Because body forces will be applied similarly. And then we can have surface forces. And these are the forces that are exerted on a fluid element by its surroundings through direct contact. So they're proportional to the extent of the area and expressed per unit area. And we generally split these into normal and tangential components. So I've got a figure for this here. So if we have this fluid element with our area dA, we see this force dF that's acting on it, and we can resolve that into its dFn, its normal component, and its dFs as shown here, which is the tangential component. And then the force per unit area we refer to as a stress. Okay, so we can write our normal stress like this and our shear stress like this. And then we have line forces, and really that refers to surface tension. And surface tension is called the line force because it acts along a line and has a magnitude that's proportional to the extent of the line. Okay, so these appear at the interface between liquids and gases, or at other interfaces, for example, between immiscible fluids. That means fluids that don't mix. And generally speaking, these won't appear in the main equations of motion, but they will enter in the boundary conditions. Okay, now if we look in a little more detail at stresses here, stresses can be completely defined with 9 components of the stress tensor. And we talked a little bit about this when we talked about second order tensors previously. So in the figure, 4 sides are shown. For completeness, I'll write it out here. Okay, and what's shown in the figure is the positive stresses. So this is how these stresses are defined when they're in their positive direction. The other 2 sides aren't shown just for clarity's sake. So the first index here shows the direction normal to the surface on which the stress is acting. And the second one is the direction that the stress itself acts. Okay, and in this example, we have our 1, 2, and 3 directions shown, and then the corresponding stress tensors, right? So 2, 1, for example, here is on a surface that has its normal in the 2 direction, right? So it's that face, but it's acting in the 1 direction right here, right? So the diagonal elements are the normal stresses we can see here with the example 2, 2, for example. The off-diagonal elements are then the tangential or the shear stresses, right? And even though it's shown as a cube, we remember this represents a point in space, okay? Now the stress tensor is symmetric, which comes in very handy. There's lots of different ways to show this. So if you're interested, you can look that up. But because the stress tensor is symmetric, there are actually only 6 independent components, right? Because it's symmetric, like tau 1, 2 will equal tau 2, 1. So instead of being 9 completely independent components, we actually have 6 independent components. All right, now we're going to look at the conservation of momentum, which is essentially a force balance. And what I'm going to do for this one is derive the differential form directly by applying Newton's law of motion to an infinitesimal fluid element. And then later we'll see how we can get the integral form from that differential form. Okay, so the opposite to what we did in the conservation of mass, so we can see how to do it directly here. Okay, so in looking at this figure, I'm going to label just a few more things. So the length of this side, right, would be dx1, the length of this side, dx2, and then this one here, dx3, just so it's really clear, right? So we're going to look at the sum of the surface forces in the x1 direction here. So we could imagine, if we imagine a little point at the middle, then we can see that this one here, for example, in the 1 direction, right, we're adding the rate of change of that shear stress in the x3 direction, right, to go from the point to the surface. and it traveled half the distance along dx3, so that's where that dx3 over 2 comes from, right? Just to make sure we're super clear on all of these terms, right? So I've got the resulting equation written here when we sum them all. And again, just to be super clear, so if we look at this surface here, okay, that's been written here, these surface forces here, and then it's multiplied by dx3, and then of course this one, we mentioned that side is dx2, right? And so that's this dx3 times dx2 is like this surface here, right? So that's why we multiply there. Okay, because the stress is the force over the area, and that dx2, dx3 is the area itself. Now we can go through, we can see that a bunch of these will cancel, right? And then we've got this one over 2 and this one over 2, so when we add them, we'll just get 1. Okay, so when we simplify all of this, we actually end up with this expression here. Which we can write much more succinctly as follows, with our summation notation, and then this is actually the volume. dx1 times dx2 times dx3, of course, is the volume of that infinitesimal little elemental cube. So the I component of the surface force per unit volume, so we've done all this for the x1 direction, but if we generalize to the I component, we see that it would actually be as follows. Reminding ourselves again that the stress tensor is symmetric, so I can switch Ji with Ij. Our body force is rho times g, where g is the body force per unit mass. And Newton's law says that the net force on the element must equal mass times the acceleration of the element. So mass times their acceleration, which will be per unit volume, which is why it's the density there. And then we have per unit volume here, right? Because we didn't include the dV down here. So for our body forces, that's per unit volume like this. And we have all of our surface forces, which we just wrote above. This gets a nice box. And this is the equation of motion that relates acceleration to the net force at a point. And this holds for anything at all, for any continuum solid or fluid, no matter how the stress tensor is related to the deformation field, which is referred to as Cauchy's equation of motion. And that, of course, is the most general case. So now we're going to look at it a little more specifically here. And hopefully you'll look at this and think, well, that wasn't so bad at all, right? We just did a force balance on a fluid element, and that's how we derived the conservation of momentum. So it's not actually that complicated to get that, right? So now what we can do is we say, okay, if we have the differential form, we can get the integral form, right? So the opposite to what we did for conservation of mass. So here we're going to look at the momentum principle for a fixed volume, okay? And we're going to get the integral form. So this is what we just derived above, differential form for the very general case. I'm going to write out our material derivative. And it's multiplied by density, so we would have it like this, with multiplied by density here. We can multiply the continuity equation by ui, multiply by ui. Now I can add ui times the continuity equation to the left-hand side of this equation. And so you see, if I group together like that term and that term, we'll end up with this one here, just using the laws of derivatives. Then I can take this one, and they will combine to give this term here, right? And then I can add the rest on like we had before, so we end up with that. Okay, now we can take each term and integrate that over a fixed region V. Okay, so this term here, when we integrate it, we'll do that down here, okay? We know from our time derivatives of volume integrals, we would have the following. And then we're going to define capital M as the momentum of the fluid inside the volume. So that's defined right here. That's why we have the triple equal sign there. Okay, so we end up with the rate of change, right, of the momentum of the fluid inside that volume. Volume integral of this second term here, let's do over here. we apply Gauss's theorem to change this volume into a surface integral, and that we define as the net rate of outflux of our I momentum, because our mass outflux would be density times uj times daj. That'd be the mass outflux, and our mass outflux times our velocity is our momentum outflux. Okay, this additional ui here. For our third term, okay, as a volume integral, that's our total body force acting over the entire volume. Our fourth term, do that volume integral over here. Apply Gauss's theorem again to go from the volume to the area. These are the net surface forces at the boundary of our volume. So then if we define F, this F here, as the sum of all the forces, sum of all our surface and body forces. So ultimately then we have all of our forces, right? So our body forces and our surface forces here. We had the rate of change of momentum inside the fluid volume and the net rate of momentum outflux for our total force balance here. And so that's the law of conservation of momentum for a fixed volume, okay? Which is what actually I teach that in my undergraduate course. And again, that's the one we use for like force balances over control volumes, which is generally what our fixed volume in space will be for engineering applications. And so that basically says that the net force on a fixed volume must equal to the rate of change of the momentum within the volume plus the net outflux of momentum through the surfaces. Okay, now it's helpful to simplify these conservation laws further, especially the conservation of momentum. So what we're going to look at now is known as the constitutive equation for a Newtonian fluid. And this constitutive equation is the relation between the stress and the deformation in a continuum. Okay, now let's think about a fluid at rest. So for a fluid at rest, there are only normal components of the stress on a surface. We don't have any shear because they're the result of velocity differences, okay? So in that case, the stress doesn't depend on the orientation of the surface, okay? So we would call that kind of stress tensor isotropic or spherically symmetric, okay, for a fluid at rest. So an isotropic tensor is one where the components don't change under a rotation of the coordinate system. And any isotropic second order tensor must be proportional to the Kronecker delta, the one we looked at before. So therefore, the stress in a static fluid, because it's isotropic, has to be of the form where P is known as the thermodynamic pressure. So that's related to density and temperature by an equation of state. For example, a very common one is our ideal gas relationship, as I've shown here, where P equals rho RT. We put a negative sign there because the normal components of our stress are considered to be positive if they indicate tension rather than compression, right? But our pressure will act in compression. So that's why we need the negative sign. If our fluid moves, okay, we're going to have additional components of stress due to viscosity. And again, this is something I go over in a lot of detail in our undergrad course, but essentially that shear stress comes from the fluid particles interacting with particles near them that are traveling at a different velocity, and that will cause that shear stress to develop. So for a moving fluid, what we can do is we can say, let's split it into two parts. So we have this part that would exist if it were at rest, right? And then we have this part that's due to the motion alone. And we'll use a sigma for that. Okay, now the sigma part's our non-isotropic part. That's called the deviatoric stress tensor. And that is related to the velocity gradients, di ui by di xj. And we can decompose our velocity gradient, as I've shown here, into its symmetric and antisymmetric parts. Okay, so now you can see we're drawing back on the foundation we built in the previous few videos, okay, and talking about the deviatoric stress tensor and in talking about decomposing this velocity gradient. Okay, now we remember from what we saw in kinematics, the antisymmetric part represents fluid rotation without deformation. And so that can't generate any stress by itself. The stresses have to be generated by the strain rate tensor, right, alone. So I've written that out here, this EIJ, that's our strain rate tensor, okay? And what we're going to do is we're going to assume a linear relationship between the strain rates and these stresses due to the motion. So that looks like this. Okay, and this K, IJMN, that I've written here is a fourth order tensor that has 81 components that depend on the thermodynamic state of the medium. Okay, so what this equation says is that each stress component is linearly related to all 9 components of our strain rate tensor EIJ. Okay, so therefore we would in theory need 81 constants to completely describe this relationship. But what we're going to show in the next few slides here is that actually only 2 of these 81 elements are needed. Okay, if we assume that our medium is isotropic, right, meaning that it doesn't have like a directional dependency, and that the stress tensor is symmetric. Okay, so we first consider that we have this isotropic medium. Isotropic really just means that there isn't a change in behavior when you look at different directions. So an isotropic medium, for example, if we were looking at, say, liquid water, has no directional preference, right? So the stresses don't change based on which direction they're acting. Okay, so that means the stress-strain relationship is independent of a rotation of this coordinate system in an isotropic medium, okay? But this is possible only if Kijmn is an isotropic tensor, okay? So that's our first limitation. And so for 4th order isotropic tensors, this is sort of a mathematical property here. All isotropic tensors of even order are made up of products of delta ij. So I can actually write this as follows. Okay, where lambda, mu, and gamma are scalars that depend on the local thermodynamic state. Okay, now this sigma ij is a symmetric tensor. So therefore, Kijmn also has to be symmetric in I and j, okay? For it to be symmetric in I and j, from this equation, our mu and our gamma have to be equal. So we write that like this. And so only 2 constants have survived of our original 81, right? Because we've restricted it to saying it's only applying now to isotropic materials and because of stress symmetry, okay? So remember, that's the restrictions that we imposed upon it, which again are very general, right? But not completely general, okay? So now if we sub this in to our constitutive equation, we end up with this. Where EMM, we remember, I'll write it here just for clarity, is del dot U, right? Which was our volumetric strain rate that we looked at previously in kinematics. So our complete stress tensor, with the static part included as well, then becomes this, and we can actually relate mu and lambda by setting I equals to j, okay? And then summing over our repeated index and noticing that delta ii equals 3, we would have this. And then rearranging, we can write the pressure like this. Now, it is possible for the diagonal terms of Eij in a flow to be unequal, right? But in this case, the stress tensor tau ij would have unequal diagonal terms because of this term that's proportional to mu in our equation above. So what we can do is we can take the average of the diagonal terms in tau, our stress tensor, and we can define a mean pressure as opposed to our thermodynamic pressure as follows. Okay, now subbing that into our pressure equation here would give the following. Now what happens is for a completely incompressible fluid, okay, we can only define a mechanical or a mean pressure because there's no equation of state to define a thermodynamic pressure, okay? Like we're missing that relationship between pressure and density there, right? So in fact, the absolute pressure in an incompressible fluid is indeterminate. And actually only its gradients can be determined from the equations of motion. Okay, now we saw from above, right, in our conservation of mass for incompressible fluids, this equals 0. Okay, so we don't have to consider that equation. Likewise, this EMM term that appears, right? That's 0 as well for incompressible fluids, okay? So for incompressible fluids, we can write our constitutive equation as follows in this much simpler form here. like that for incompressible, and make sure you just note that that's for incompressible. Where P can be interpreted as the mean pressure because there's no difference between P and the mean pressure. Okay, but for a compressible fluid, we can define a thermodynamic pressure. So it seems that P and this P bar, this mean pressure, could be different. But actually we can relate this difference to the rate of expansion through a proportionality constant we introduced, known as kappa, which is called the coefficient of bulk viscosity. Okay, and that's written like this. Okay, now in principle, kappa could be measured. However, in practice, it's not really practical because you need huge values of our d rho by dt material derivative to make the measurement. So really, in a lot of applications, we assume what's called the Stokes assumption, which says that this is equal to 0. Okay, and in many cases that's found to be sufficiently accurate. And it's also seen to be supported by what's known as the kinetic theory of monatomic gases. Okay, and this is something you can dive more deeply into if you want to as well, but that's as far as we're going to take that in this course. Okay, now if kappa is equal to 0, right, what happens is this lambda here becomes this 2/3 mu in our stress tensor right here. That would be the substitution there. And then we end up with a linear relationship between tau and E, and that's consistent with how Newton defined our viscosity coefficient in simple parallel flow. So if we sub in that 2/3 mu, we end up with this stress tensor relationship here, and fluids that obey that are known as Newtonian fluids, and that from which that results in our shear stress definition, that this famous Newton's definition of viscosity coefficient in a simple parallel flow where the velocity u is only a function of y. And our fluid property mu here can depend only on local thermodynamic state. Okay, so this one can be boxed. It's probably important enough to have our stress tensor for a Newtonian fluid. And then we look at this, so our non-diagonal terms are of the form like this, like tau 1, 2 would be mu times diu1 dix2 dix1. That relates shear stress to strain rate, right? Diagonal terms are a little less clear. So for that, they would be like this, for example, is an example of one. So tau on 1, so we're looking here at a normal stress on a plane normal to the x1 axis. And so we see it has these two components. The first term there's the pressure, which we'd expect. But then you add this other term, which is this normal viscous stress, which we can see from this equation is proportional to the difference between the extension rate in the x1 direction and the average expansion rate at the point, right? And therefore, you only get these normal viscous stresses if you have extension rates that are different from the average, okay? And that's what I've written down here in summary of that. Remember, you can also be taking your own notes for this alongside what I'm writing. And that really helps you to sort of understand this more deeply and retain this information. And of course, our normal forces don't just include the normal viscous stress component multiplied by the mu there. We also have the pressure term, of course, which is commonly where our normal stresses come from. Okay, and now basically we're going to move on from here to look at how do we get the Navier-Stokes equation from these more general conservation of momentum equations. Okay, now we want to get our equation of motion for a Newtonian fluid. So what we do is we can sub that constitutive equation we just derived into Cauchy's equation that we derived before that. And we end up with this equation here, where we've noted that when we subbed in that this was true, because we saw how our Kronecker delta could switch the index, right? So this is a really general form of the Navier-Stokes equation. Viscosity, mu in this equation, can be a function of the thermodynamic state. And for most fluids, this mu is a function of temperature with a fairly strong dependence. It decreases with temperature for liquids and increases with temperature for gases usually. However, if the temperature differences are small within the fluid, then we can actually take mu outside of the derivative. And this reduces it further to the following. These mu's right here, right, can be taken outside like this. And then we use the Laplacian, which is shown down here, okay, to further simplify that and put mu outside of these brackets. So that's the rearrangement we see for this general form usually. Okay, now all of these are important, right? They're just simplified forms. So in this case, we've assumed small temperature differences, right? So we were saying mu won't change by very much. Then we make a further assumption, which is very common because we look here, we see that we remember for incompressible fluids is 0. Okay, so that makes a really nice simplification on this. So for down here, where the del dot U is 0, right, from our continuity equation, conservation of mass for incompressible fluids, the Navier-Stokes equation reduces to this form right here, which is a much more simple form for incompressible fluids. And we see from visually just how much easier that's going to be to solve and work with mathematically. So that's the Navier-Stokes equation for incompressible fluids. And if our viscous effects are negligible, right, then we end up with the Euler equation, because we wouldn't have that term with the viscosity in it right there. So the Euler equation would be this one here. I use a circle for that because we really want to box the Navier-Stokes equation for incompressible fluids. Okay, so now that we've seen how to derive that, we know what it means, we know where it comes from, we know what assumptions have to be in place for us to use these equations and when we use which one. And now also, if you have more complex scenarios, you can go ahead and derive a different equation of motion with these conservation laws yourself, right? Okay, and that's really powerful in fluid mechanics. So we're going to stop there for video number 4. So in summary, in this video, we looked at the conservation laws. So we looked at a little bit of math that was necessary for us to derive those laws, specifically Reynolds Transport Theorem. Then we looked at the conservation of mass and the conservation of momentum. And we saw that the conservation of momentum is actually a force balance. How to derive them in their most general form. Then we applied a few different assumptions to get them in more specific forms where the math is a little more simple, okay, like the Navier-Stokes equation. We also did that by looking at our constitutive equation closely, which is the relation between the stress and the rate of strain in a fluid. And in the next video, we're going to look at a few more of these conservation laws and then a few more approximations and some boundary conditions, and where we'll finish up section 3 in the next video. So that's all for this video. Thanks for watching.